Could Lake Mead, the giant reservoir that quenches a quarter of the United States population, lose another 20 feet of water in the coming year? What if a new federal plan to protect upstream supplies accelerates that plunge? Science lovers may wonder what natural forces really govern the height of this lake. The answer lies in geology and hydrology, not politics. It is the snowfall, heat, geology and water cycles of the Colorado River Basin that ultimately determine Lake Mead's fate. If those elements stay dry and hot, the lake will continue to shrink, perhaps to unprecedented lows, no matter who flips the bureaucratic switches. Lake Mead is enormous, one of the largest man-made reservoirs in the world. Formed by the Hoover Dam on the Colorado River, on the Nevada and Arizona border, about 40 kilometers, about 25 miles, east of Las Vegas, it stretches roughly 180 kilometers, about 112 miles, upstream, and covers hundreds of square kilometers at high water, about 593 square kilometers, or 229 square miles, when full. At full pool, it holds about 31 million acre-feet of water, roughly 38 billion cubic meters. Those numbers are hard to picture, but it means the reservoir at its peak could cover Manhattan 5 times over to a depth as tall as the Empire State Building. Today, however, Lake Mead sits at only about a third of that volume. In mid-2022, it fell as low as 27% of capacity, the lowest level since the lake was first filled in the late 1930s. By spring 2026, it had bounced slightly to roughly 35% full, still far below historical norms. That equals an elevation around 1,044 feet, about 318 meters above sea level, which is only about 12% of the way back to full pool. Natural forces explain why. Lake Mead's water budget is dictated by the Colorado River's geology and climate. Nearly all of the water comes from the Rocky Mountains. Scientists estimate that about 96% of the lake's annual refill is due to snowmelt in the Rocky Mountain headwaters. Each spring, warm weather melts winter snowpack, swelling the Colorado River, which feeds Lake Powell and then Lake Mead. If that snowpack is low, for example, because a winter was unusually warm or dry, far less water will flow downstream. Just as important, the southwest's hot, dry climate robs the lake of water through evaporation. About 800,000 acre-feet of water evaporate from Lake Mead every year, roughly 1 billion cubic meters, which is on the order of 10% of the entire lake's capacity annually. Any increase in heat or sunlight makes this loss worse. As one researcher notes, the water flow out of and evaporating from Lake Mead has consistently exceeded the amount of incoming water in recent years. In other words, Lake Mead is shrinking primarily because more water is leaving to evaporation and outflow than coming in from upstream. Over the past few decades, persistent drought and a growing regional thirst have kept withdrawals high, while nature's supply has dwindled. The data paint a stark picture. In July 2022, when 2 decades of dry weather hit a critical point, lake levels plunged to depths unseen since Hoover Dam was built. Satellite images from that time show a dramatic bathtub ring, a chalky white band of minerals on the canyon walls, marking where water once reached. Officials recorded the water elevation as low as 1,041.3 feet, 317.4 meters. Above sea level, only about a quarter of the original 1,220-foot, 372-meter full pool. By comparison, in July 2000, a wet year, the water was at 1,199.97 feet, 366 meters, nearly full. This swing shows how sensitive the system is. The lake's level now is only a few feet above its all-time low, recorded in July 2022. Federal projections even foresee new record lows by late 2027, potentially reaching around 1,032 feet, 315 meters. We should ask what effects could cause another 20 feet of drop. One factor is policy. In April 2026, the Bureau of Reclamation announced a plan to protect Lake Powell, upstream, from plunging below its minimum power generating level. To do so, they will cut releases to Lake Mead by nearly 20%, from about 7.48 million acre-feet to 6.0 million acre-feet for the coming year. In simple terms, less water will flow downstream into Mead as a result. That means Lake Mead effectively loses up to 1.5 million acre-feet, about 1.85 billion cubic meters, that it would have otherwise received. If the weather remains as dry and hot as it has been, hydrologists warn this could indeed drop the lake by on the order of 12 to 24 feet in the coming year. The Southern Nevada Water Authority, for example, estimates that under current conditions, Mead could fall another 16 feet, about 5 meters, by year's end, and an extra 9 feet, about 2.7 meters, of shortage cuts could drop it even lower. Some independent analysts doing the math on water flows arrived at roughly 20 feet of additional decline over the next 12 months if the reduced inflows coincide with summer heat. In practice, each foot that Lake Mead's surface declines translates to hundreds of meters of new dry ground exposed along the shores. To appreciate why 20 feet is a huge deal, remember that each foot of water depth represents a vast volume spread over a wide area. Lake Mead's surface is larger when full, roughly 593 square kilometres, and still hundreds of square kilometres even at one-third capacity. 1 acre-foot, about 1,233 cubic metres, is enough to cover 1 acre 1 foot deep. So losing 1 million acre-feet might sound like a lot, but the lake's catchment area is on that order. For rough scale, studies note that a drop of just 20 feet, about 6 metres, can shift the shoreline inward by about 600 feet, nearly 180 metres in places. That translates to vast new embankments of dry land, formerly deep under the water. On Lake Mead's eastern arm, channels and coves that once were 100 metres, about 328 feet, below water are now dry or trickling. Boat ramps have to be extended by hundreds of metres to reach the receding water. New springs and mudflats appear. All told, the lake's bathtub ring grows wider by dozens of metres with each additional foot lost. Key hydrologic factors driving Lake Mead's level include the Rocky Mountain snowpack, evaporation, groundwater interactions, rising temperatures and drought, and demand and supply imbalance. Nearly all of the lake's inflow starts as snow high in Colorado, Utah, Wyoming, and New Mexico. In a wet spring with heavy snowmelt, the reservoir replenishes. In a dry one, it does not. Scientists estimate about 96% of Mead's water comes from runoff of mountain snow, with only roughly 10% coming from local rainfall or groundwater. Thus, unusually low mountain snow, as happened after the warm, dry winters of 2020 through 2023, starves the lake. Evaporation remains intense in the desert climate, removing about 800,000 acre-feet, about 1 billion cubic metres each year. Groundwater exchanges also play a role as the reservoir and nearby aquifers are connected, allowing water to move underground as levels drop. Meanwhile, climate warming has increased temperatures across the basin by more than 2 degrees Fahrenheit, over 1 degree Celsius since 1980, reducing runoff and increasing evaporation. Historically, water agreements assumed about 17 million acre-feet, about 21 cubic kilometres, of flow per year, but actual long-term flows average closer to 14 million acre-feet, creating a structural deficit. Put together, these factors explain Lake Mead's recent history. In wetter decades of the 20th century, the reservoir often approached full capacity. But since about 2000, a prolonged drought has reduced inflows dramatically. Tree ring studies suggest this dry period may be the worst in over 1,200 years. The result is a steady long-term decline in lake levels, even as demand remains high. Regulation by upstream dams has smoothed short-term fluctuations but has not reversed the overall downward trend. So, is the new policy a mistake? From a geological standpoint, it simply accelerates an ongoing process. By diverting extra water into Lake Powell and away from Mead, managers are effectively reducing Mead's inflow further. If we imagine Mead as a bathtub controlled by a faucet and a drain, the faucet is being turned down. Even if this helps the broader system, Mead itself will show the loss. Current projections suggest that without an unusually wet year, Lake Mead will continue to decline and may reach new record lows by the late 2027 period. Importantly, this all comes down to water, not politics. The same natural forces would have driven Mead downward regardless of policy choices. Satellite observations show the land beneath the lake slowly rebounding as water weight is removed, while nearby aquifers respond to changing pressure. Water that evaporates or flows out is effectively gone from the system. The root cause remains simple: less snow, more heat, and higher evaporation. What would it take for the lake to rise again? It would require a sustained period of unusually high snowfall in the Rocky Mountains, followed by favourable melting conditions. Large storms delivering significant precipitation could temporarily reverse the trend. Until that happens, the trajectory remains downward. As of 2026, Lake Mead is only a few tens of centimetres above its lowest intake levels, highlighting how close the system is to critical thresholds. In short, the geological and climatic story of Lake Mead is relentless. A hotter, drier basin means less water year after year. Policy changes can redistribute water but cannot create new supply. Unless climate patterns shift significantly, the lake will continue to recede. The conclusion is clear: the decline of Lake Mead is driven primarily by natural processes, and any additional drop, including another 20 feet, is entirely plausible under current conditions. That downward trajectory matters not only because of the lake's size, but because of the way a reservoir behaves once it falls through certain thresholds. Large lakes do not decline in a smooth, uniform manner. They cross critical elevations where consequences multiply. A few feet, about 0.3 meters, can mean the difference between water reaching a pumping intake or leaving it stranded in air. A few more can expose previously submerged sediments, intensify evaporation from newly widened shorelines, and alter the chemistry of the remaining water. In that sense, Lake Mead is not just losing depth, it is changing state. One useful way to understand this is through feedback. As the lake falls, the exposed reservoir basin grows hotter under direct sunlight. Darker shore sediments absorb more heat than water, and that heat radiates back into the local atmosphere. The result can be a warmer basin, more evaporation, and more stress on the shrinking water body. At the same time, lower water levels can concentrate dissolved minerals, making the reservoir more saline and less hospitable to aquatic life. What begins as a hydrologic shortage becomes a physical and chemical reorganization of the lake itself. The shoreline is not simply moving, the lake is becoming a different kind of environment. This transformation is visible in the broad pale band that now rims the canyon walls. The so-called bathtub ring is more than a dramatic symbol. It is a geologic record written in calcium carbonate and oxidized sediment, a visible marker of former water levels. In places, old beaches, delta deposits, and submerged terraces are emerging again, revealing the basin's long history of flooding and drying. Those features remind us that Lake Mead sits inside a landscape that has never been static. Over geologic time, the Colorado River has cut its way through uplifted terrain, carried sediment from the continent's interior, and built and rebuilt deltas in response to climate swings. The reservoir is man-made, but the basin it occupies is ancient, and its behaviour still follows the logic of the surrounding land and climate. That is why the lake's future depends on more than one wet winter. A single snowy season can produce a temporary rebound, especially if reservoirs upstream are managed carefully and summer heat is moderate. But a one-year recovery does not erase a structural deficit. The Colorado River Basin has entered a period in which average demand remains higher than average supply, and that mismatch is the fundamental reason the system keeps sliding towards stress. Even when the reservoir rises a little, it often does so from a lower baseline than in previous decades. The trend line matters more than any one month. Another part of the story lies beneath the surface. Groundwater systems surrounding Lake Mead and the Colorado River are not isolated from the reservoir. As the water level changes, pressure gradients shift, and water can move into or out of adjacent aquifers. In some zones, the lake may recharge nearby groundwater. In others, groundwater can seep into the reservoir. This exchange is slow compared with river flow, but over time it influences storage, shoreline stability, and the behaviour of springs and seeps along the margins. When the lake recedes, it can also trigger collapses or slumping in saturated banks, further reshaping the coastlines and complicating infrastructure planning. The consequences extend far beyond geology. Cities, farms, and tribal communities throughout the basin depend on this water. When the reservoir falls, the problem is not abstract. It becomes a question of intake elevations, delivery contracts, crop choices, and emergency planning. Municipal systems need enough head pressure to move water efficiently. Irrigators need reliable seasonal allocations. Power generation at the Hoover Dam depends on sufficient hydraulic head. Each decline in the lake level tightens the operating margin for these systems, forcing managers to choose between competing risks. The reservoir is therefore both a natural archive and a machine, and when one part weakens, the other becomes harder to run. What makes Lake Mead especially revealing is that it sits at the intersection of climate and engineering. The basin records what weather has done, but the dam records what people have tried to do about it. Reservoir operations can buffer year-to-year swings, yet they cannot defeat a prolonged reduction in runoff. In years when snowpack is thin and temperatures are high, there is only so much that release schedules, conservation rules, and upstream coordination can accomplish. Human management can redistribute water in time and space, but it cannot make snow fall in the mountains. That is the hard limit the system keeps running into. So the question is not whether Lake Mead will ever rise again. It almost certainly will, at least in some years. The real question is whether the basin can sustain a new equilibrium in which inflow, evaporation, and demand are closer to balance. That would require not a single unusually wet season, but a sequence of wetter years, cooler conditions, and lower net withdrawals. It would require the Colorado River to behave less like a shrinking pipeline and more like the resilient mountain-fed system it once appeared to be. Whether that happens is uncertain. For now, the lake remains a powerful indicator of regional strain. Its falling level is a signal written in water, rock, and heat. It tells us that the Southwest is living within a tighter hydrologic budget than the one its infrastructure was designed for. It tells us that climate variability, amplified by warming, can overwhelm assumptions built into old water agreements. And it tells us that the landscape itself is responding in real time, exposing its terraces, drying its coves, and inching toward a new form. Seen this way, Lake Mead is not merely receding, it is revealing. Beneath the shrinking waterline lies a story about geology, climate, and human dependence that was always there, waiting to be read.